Let's see. I just want to make sure everyone's ready and pumped for this, because I'm excited, and I want you to be excited. So, okay, we're all here. We're all awake. Check. All right. So, this is the thing that we always end up with in our software architectures. We have the big ball of mud. Have you heard this phrase? So, you know, it's describing what was once very well separated, clearly defined, ice cold and sharp, now has become all smushed together and messy, and we're not quite sure what's going on. Why isn't it working anymore? It's doing things it didn't do before, and now it's doing things because somebody somewhere did something, or I don't know what. And it's not fun to test anymore. It was fun. It's not so fun anymore. Or we have to hire some other group, some new team, some new people to test it because we just don't want to even test it. We don't even want to go there anymore. But we need to test it. So this happens because of a lot of reasons, but basically entropy. Entropy happens. We're mixing things together, and we mix the water and the dirt, and we get mud. So what do we do? How can we try to solve it? We have to do something. This is what we do, and it's embarrassing. So what the architecture astronauts say is we must decompose. Yes, we must decompose, and we all agree, because of course, who doesn't want to decompose? Of course, we must decompose, and we want to. We want to decompose because there's good things when you can decompose. Things aren't so icky. Things aren't so messy. Things are clearer. But what do we decompose them into? Things that compose. Like, I don't think we can answer this question. Like, what do we decompose into? I want to know what the shape of the thing that we want is. So we can agree on the direction that we want to go in. We must decompose. That's the direction we're going to go into. But I don't think we have a good story or a vocabulary around what we're going to make. What are we going to decompose into? What are these composable things? So that's kind of the motivation of this talk. I don't know what to do. So that's the hypothesis here. So I don't know what we're going to decompose into. But I got an idea from reading some books and thinking about things and getting a bloody forehead against my desk, mostly stealing ideas from other people. And that idea is algebra. Algebra. Algebra is the thing that I'm going to talk about that I think is what we're going to decompose into, that we're going to compose together. It's the composable thing. The composable thing is algebra. So what's algebra? Okay, we're going to talk about that. So we're going to talk about what is algebra. Why am I bringing up this word? It has some structure that we're going to figure out, and we're going to use it. Then I'm going to add another word in front of algebra, and it's going to be domain algebras. So I'm going to try and connect this general idea to the messy world of our programming where we're in domains. You know, your domain, my domain, the domains of our customers, etc. We're going to make sure that we can test it. We're going to have some composable thing, but we got to actually like implement it. So maybe a little implementation detail, and that's going to be the talk. All right. So algebra. I don't know. What are we talking about by algebra? Well, here's an algebraic thing that we can probably all read. We've been trained to read what this is and means, and that it kind of works. We have symbols, and we can add things, and we know like A must be some variable or something, and B is a variable, and we can do things. So high school kind of algebra. Okay, so that's definitely an algebra. But we don't just do that in our programming. There's a different kind of algebra, Boolean algebra. So we learned about this when we were learning about programming. We know how to combine these expressions. We and we not, and we De Morgan, and we flip things. And I still kind of I'm not so great at doing De Morgan on my ifs analysis and things. But that's why we have computers. So here's something that's a little different. This is my artist's rendition of a Lego. So what do you get when you put two Legos together? You get a Lego. And you can use that Lego with another Lego. So it's a very composable thing. We love to talk about composition and compositionality in functional programming, but it's not a very necessarily well defined in some senses. But Legos, yeah, you can combine them together, and there's certain things that you can do and you can't do. So a 2x2 and a 2x2 can, if the dots and the whatever the dots go into match, then you can make something. Otherwise, you can't put it on. You can find creative ways, but there's some configurations that just don't work. So they only combine in some mostly fixed way. So Legos are cool. Here's something that's more programmery. So this is kind of like a DSL, domain-specific language. So in the middle here, sorry, I won't get so close. There's a quarter of a circle. It's an arc, and if I rotate that some multiple of 90 degrees, if I do that 0 to 3 times, aka 4, if I do that 4 times, if I do 4 arcs in a path, I can draw a circle. So we kind of have like expressions, and expressions are made of other expressions. And I can combine them and manipulate, and that can be equal to some other thing. And I can draw a figure on a screen or whatever I'm drawing on. I'm going to say that this is also algebraic. And then what about types? I love types. I can't stop talking about types. We build types. We build types out of other types. An address could be a street and a state and a zip code or whatever. Like, I have this new type that's built out of other types. And there's different ways to do that. So I can combine types, I can make new types, I can take them apart, I can put them together. Something similar. And then what about an API? So like this is a snippet of the Github Commit Api, where you can get and push commits, via a REST interface. So this is kind of the REST form of an API. We can maybe an API can be kind of an algebra or an algebraic thing, which means I can kind of do something with it. I can maybe make my APIs like Legos. That's all of our dreams, I know. So those are some examples. What's common about those things? So I'm gonna say that an algebra has some structure. So we're gonna use the most familiar one. So what are the parts of these things and how do they interact? So we have our expression here, and we have some variables. We've got some constants. Those are kind of the nouns, the things that we're manipulating. We can perform various operations on them. We can add them, we can multiply them. And then everyone's favorite part, they're all the laws that we learned in 7th grade or whenever it was. If you add 0 to a number, you get the same number back. If you multiply by 1, you get the same number back. It doesn't matter if you add this way or that way. We've internalized them, but sometimes we get to write them out. Sometimes we read it in the math book. So I'm going to say that an algebra has these 3 parts. There's going to be some symbols, there's going to be some operations, and there are going to be laws that govern how they interact. You don't multiply 2 numbers and get a donut. You multiply 2 numbers and you get a number. So in our arithmetic example, we have this. And usually the laws, if they're more mathematical, they have fancy words like distributivity and commutativity and associativity. But we're going to try and use the same concepts to describe the laws of what we do. So this comes to domain algebra. So I want to take this idea of an algebra with symbols and operations and laws and use it in my software development, in my modeling task, in my the clean thing that I'm going to compose. So a domain is what we do. We work in domains, and then we model them in our programs. So we have accounts and shopping carts, and what else do we have? We have users and authenticated users and unauthenticated users, and we're modeling the things in our business. And they interact. You can check out your shopping cart. You can do all the normal examples. So if I'm going to map to this algebraic schema, the symbols, I think I know what those are. Those are like the entities. Those are the entities that are my users and my carts and my accounts and my delivery and all those things. What about the operations? Well, these are just the behaviors in my domain. You know, you can check out your shopping cart. You can deliver an item from one warehouse to another. You know, our business logic. And then the laws. Well, these are the rules that say, well, you can't have -1 items in your shopping cart. That doesn't make sense. Or all those boundaries that describe, well, you can perform some operations, but only in this context. So I'm going to sort of try and convince you that we can have this algebraic structure, say, on the Github Commit Api. So here are the sort of REST endpoints. So there's 2 of them. There's a get and a post. And so we have, oh look, we have some entities. We're talking about, I want to get some commits or push one up. So I'm talking, and there's an owner involved. There's the repository that I'm talking about. There's the commit. Commits have SHAs, which are the hash that a commit is identified by. These are our entities. The behaviors that we're exposing on these entities are we can get commits and we can post commits. Business rules, I'm not quite sure yet. What are sort of the boundaries? What are the limits? What can you do and not do? All right, so we're at a Scala conference. Let's make this into, how do I encode this algebra in Scala? I'm going to do it in a very particular way that I stole from Devashish Ghosh. I'm going to start by making an abstract trait. Ta-da! Look, it's an algebra. Trait GitHub commits. Now, it's a trait because I want to specify as little as possible. So I'm going to be talking, I want the interface, not the implementation, as much as possible. So trait, easy choice there. Okay, then I'm going to take all of the entities in my domain, and I'm going to turn them into type parameters. Okay. Why type parameters? Well, I'm going to have a little detour. So there's lots of options here, right? They could be type parameters. They could be referencing some type somewhere else. They could be referencing a type. We could have the types inside of the trait, sort of inner type. They could be type members rather than type parameters. Or they could reference some real type. Well, we have type parameters. So those are an instance of abstract types. Like if I am writing what the trait GitHub commits is going to do, I don't get to choose what those are. The implementer is going to choose what those types are. So they're abstract types. So as a digression for why, and I have a little quiz. Don't worry, it's really easy. If I had this method foo that takes a type parameter, a, and I want to input a string and return an a, how many possible implementations of this could I make? Well, who wants to, anybody? I'll just shout it. Like, if I was writing this, how could I write this? What would be?
No.
No, okay, we're not going to allow nulls. I can't believe you said that. We're Scala programmers, we don't use no.
Nothing.
Nothing. Well, nothing meaning you can't do it.
No, that's the value.
You can't produce a value of type nothing. That's why nothing is cool. Well, you're close. I mean, you're on the right track. There's no way to write this function. So that was the freebie. I gave you that answer. Right? Because I don't know what A is. So how can I make an A? I have to return an A. But I don't know what A is. I can't write that function. The only thing I can do is blow up. Okay, so what about this one? I'm given an A. How do I return an A? Identity. I just return the thing that I got. There's only one way to write this function. Again, I don't know what A is, so I can't like call a method on it. I can't pass it to some function which does something to it. I don't know what it is. So there's only one way to write this function. What about this one? I'm given two A's and I need to return an A. So there are two. I could return the left one or the right one. And that's it. Again, I don't know anything about A, so I can't do anything with it. I can't call a method on it. I can't pass it to anything else. Nothing. Okay, well, here's the other end of the stick. I'm given an A, but I need to produce a string. How many ways could I write this function? One? Infinite, yeah. If you do that, I'm going to say one because I don't hear you. Yes, well, almost infinite. I mean, the size of string, right? Which is infinite. So what am I trying to say here? I'm trying to say that when you have type parameters, these are just names. They're names of types. I know nothing about them. So back to our, I'm given an A. Well, I'm given something. I need to produce it. There's no way I can't do anything. I can't do it. There's only one thing I can do here. If I don't know what these types really are, then I can't really involve them in the methods that I'm going to define next. So that actually reduces like the surface area of my API. I can't go wrong by calling some method on a type. There's less ways to kill myself. I'm gonna try and repeat that as we go forward. But because it's somewhat unintuitive that we're opening up our algebra with these type parameters, but we're actually making our algebra much safer because there's so much less that can go wrong. Because I don't know anything about these types, there's nothing wrong. I can't do anything bad with them. I can't implement something wrong. So I want to make my algebra like as bug-free as possible. So the less I can get wrong, the better. Okay, so that's the end of that sidebar. So we have these type parameters. Those are the entities in our domain. And then our behavior are just going to be abstract methods. So I'm going to translate those REST calls into some abstract methods. They're going to take input parameters, and they're going to produce output parameters. Outputs, they have types. You know, we didn't quite, the REST API is hiding a little bit the optionality aspect of if you ask for a commit that's not there, you know, you'll get a 404. It's sort of implied in the REST contract there. We're exposing it as a method here, so we have to encode it a bit more clearly. But nothing unexpected. And what have we made? We've made an abstract interface. It has a particular structure with the type parameters, but it's an abstract interface. Easy peasy. So this is what I'm just going to, this is an example of a domain algebra. So its symbols, these are going to be those abstract types that represent the entities. The operations are going to be these functions that act on them. Maybe they have some effects associated with them, future, option, either. We can sort of use those things. But what about the laws? Like, what are we gonna say about our API? Like, what invariant must we maintain? So I'm going to jump into that a little bit. So here's our algebra again. I'll give you one for free. So what do we want to be true? Like, we're going to write tests, and we're going to say what must be true. So I think one thing that must be true is when you push a commit up and you read it back, you should get back the same thing. Otherwise, the world would be very confusing. So if I do a get after a create, I should get the same object back. And we have when we write our tests, this happens all the time. We're like, when we we turn something into JSON, and we turn it back into the thing from JSON, and it's got to equal the thing that we started with. This is the same idea. So we would encode it, somehow like this. So we do a create operation first. The output of create is the SHA. So then we put that in as the parameter in the Git, and we should get back the commit that we pushed up. Another one I think that should be true, that I'm not quite sure is the right encoding of it, is using a big fancy word, idempotent. So if I create the same commit twice, it should be the same as if I created it once. Like committing it more doesn't change anything. I'm not sure about the encoding of it, but I can sort of naively encode it this way. So I run create once, and it should return the same as the second time I do it. Maybe I should involve get, I'm not quite sure. But we kind of want to represent, that it's an immutable world. So I've had those Boolean properties. Okay, well, I'm going to lift those up into some interface to test with. So I'm going to make the GitHub commit laws. That's going to be another abstract thing. It's going to be a trait with type parameters. And it's going to contain the algebra that I made that has the other type parameters, and they're going to line up. And then I can write some functions that exercise and sort of demonstrate those laws. So I have an API in the GitHub name, and I call create, and I pass the output to Git, and I should get the same commit back. So this is the basis of your unit tests. So when I have a particular implementation, which I'm going to get to next, all my implementations can be run against these laws. I could use the Scala test matchers to make it look a bit nicer and print better error messages. But essentially, I'm asserting what are the properties that must hold. And note that the properties are sort of intertwined. Or not the properties, but like I can only talk about Git in the context of create. And they're like, I can't talk about one without the other. They don't. It's sort of a weird property, or it's sort of a weird notion. But all of our business logic are sort of self-referential, and they all sort of talk about in terms of each other. And so you can decompose a system like that and figure out what's really dependent upon what. There's this implicit contract that's encoded there somehow. So the laws, they can become property-based tests. See also in my workshop. But when we start with an algebra, we have our entities, we have the methods that act on them. We naturally will produce property-based tests. So then we can take advantage of frameworks like Scala check. We can write generators which produce data to test so that we don't have to do it manually. And we get sort of more powerful tests. We're saying for all the inputs that I could provide, this must be true. And that's, again, the more abstract that you make the types, the less you can assume, so the fewer bugs that can be. So I've had some abstract things. I've had abstract, the trait, the algebra itself is a trait. The tests where the laws were, that's a trait. Okay, how do I actually implement this thing? Well, nothing surprising here. It's just we have our trait, and then we implement it. So here's a really dumb way to implement it with a mutable map, of course, for my repo. But any kind of implementation, whether it uses resources like memory or a remote service or some I/O storage, persistence system, is going to have the same kind of shape. We're going to implement the methods that need to be implemented. We're going to define the types, but now we can actually specify what those types are. So for this particular interpreter, I just made some simple case classes to represent the entities in my system. So the owner actually has a property called a username, and the repo has a name, and a commit has some properties of a SHA, and maybe the blob of the commit is stored as a bunch of bytes. The algebra didn't know about any of those details, but they're only important in terms of the actual implementation. So they're just implementations of this abstract thing. and they implement the behaviors of our algebra, and they have to satisfy the laws, because that's our guarantee that our algebra is written correctly. So all those together make it really nice. But then, if you squint your eyes a little bit, you could use, in your implementation, you could use some other algebra. And in fact, we already do. This is where the composition comes in. You can, if an algebra has this structure, if it's a bunch of symbols and operations and some laws governing it, we can view option as an algebra, right? So option, there's some rules about options. If I call get or else on an option, if it's a sum, I should get the thing in it. Otherwise, I'll get the parameter to the get or else. That's the law of get or else. That's the get or else law. Let's call it that. And conversely, if my option was a none, I will get the argument passed into get or else. That's really what it is. Option, the entities are the sum and the none, and the things you put in them. The behaviors are like the get or else. You can map, so you can make the map rule. Other things have maps, so we can start to abstract that. So we're building algebras on algebras. Now, these algebras, there's nothing, I haven't created anything new, anything novel. I stole the idea, so I can't say I created anything. But these algebras, they're sort of this minimal set of attributes that I want to say, like, as something I'm going to decompose into, that I'm going to compose together. And I think the algebra has the necessary, but only the necessary parts for making composable systems. So I think algebras are the right form. They're the answer to the question of what should I decompose into. So that structure of the operations, the symbols, the laws, it carries just enough power without specifying any of the concrete details. So it's a nice way to separate the thing that I want, and then I can hide everything else so I don't get the blurry, muddy effect with the entropy won't affect us so much, and we won't get the big ball of mud. So it's fine to take this mathematical idea and run with it. We need to put it in terms of that we develop with. So the symbols of this algebra are just the nouns, the operations of the verbs, and our business rules can really encode the laws of this algebra. And then the implementation just falls out from there. I think it's more of this idea is more of a discipline and a particular implementation, but it has very good sort of properties in the future. We can get property-based tests, and we, at some point, need to specify what these things really are, but it's separated from everything else. So I'll close with this quote, which is always a good one. So when we're abstracting, the purpose is not to be vague, but it's to create a new semantic level in which we can be absolutely precise. So the idea is that perhaps the algebra, as was described, is kind of a form which allows you to have that precision and properly abstract, where you're actually nailing something down, and this is what it is, and this is how it behaves. This is what are the expectations about it, without any other details. So thank you very much. I'm happy to answer questions now or later. And most of this material is from Debashish Ghosh's book, which you should buy. It's really good. It's called Functional and Reactive Domain Modeling. He goes into all the details, sort of how to do this. I gave you the quick version, but it's a really good book, and it's very functional, but it's also very, very sort of practical. And how do we do these things, and what's important about it? Why should we do this? And he'll go through all the examples. So thank you very much. Any questions? Can't wait. I will algebra. You can raise your hand.
I have one question.
Yeah.
Other than algebras, have you explored any other mathematical structures that you think you can apply to programming as well?
Oh, well, so are there other mathematical structures? Well, the thing is that I mean, there's all these mathematical things that are baked into various libraries in Scala, and you'll see them more in Haskell and things, and or there's libraries like in Scala it'd be Cats and Scala Z and Spire. So there's like the semi-groups and monoids and so on and so forth. Those are algebras, but I think I felt like that, and those are fantastic, and we need more of these ideas. There's group theory, there's everything from abstract algebra, but I think we don't often program in that world. There's certainly times when we need to know about the algebraic, more mathematical algebraic structure of what we're working with, but it doesn't come up very often when we're building our web service to read some JSON and send some JSON somewhere else. So I wanted to kind of find some bridge between that mathematical world and what we deal with more. So I'm trying to say, yes, we need more of it, but we kind of need to bridge that structure up into the messier world that we deal with. Yeah.
Sorry. When do you need to define more complex algebras, like something that implies asynchronous operations, and now your algebra has some futures defined?
Yeah.
And this is where comes into play like the free monad, free pattern, when you can also abstract that object that is now defined in your algebra.
So you're asking, is it the same, or is it equivalent to a free monad kind of implementation, or?
I'm just asking if that will be the next step after defining just the algebra to the free pattern to define a more.
Well, so if you have if I just have this abstract thing, so what would be next? Well, so you can imagine that I didn't really capture error handling. I didn't really capture asynchronous processing. So what you can do is then you can make the container type a new type parameter. So you would pass in an F with a hole in it. That would be the future or either. And then it would return an F of option commit, say, and you can sort of parameterize the effect. So I didn't get to free, but if you parameterize the effect, then you kind of have another lever to play with, because all the implementation of this algebra would have to choose what effect that they live in. Some would be synchronous, some would be asynchronous, some would have error handling, some would not have error handling. But all the laws would still would be independent of those effects because there are type parameters passed in. So you can say, well, I want this to be asynchronous, blah, 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 and you can pass that in. Where you go now, I mean, I'll probably, we can take it outside the talk, but like the free monad, or making that is just it's sort of the dual of this representation. So we have our operations that are parameterized by some types, and there are methods here, but it's easy to turn code into data. So we can make a get object and a create object that take the arguments and have a return type, and then we can lift that up with the free monad. So they're really two sides of the same coin. But I think one thing that you're pointing out is that there's the separation between the interface and the implementation. There's the language that we're writing our program in, and then there's the interpreter about it. So we're separating those, and it can be implemented both ways. Anything else? All right, thank you very much.